Good day. Welcome back to the fifth and final part of our discussion on differentiating inverse trig functions. And before jumping into a recap of the associated class worksheet, I wanted to go through one more example involving a definite integral because it involves a nice technique. So if we encountered this integral from 0 to 1 of x over 1 plus x to the fourth, this is a rather difficult integral until we see how we can rewrite the integrand to make it a bit simpler to handle. And my thought process or intuition working through it is I don't know the antiderivative off the top of my head. It does not directly compare to any of the common formulas that we've encountered, so somehow I would like to do a substitution. And if you were to do a substitution, it would be really nice to have that x dx play the role of du. And what I want you to think about for a moment is in order for du to be x dx, what would your choice for u have to be? And note, I might not write down precisely what it is, but if u is x squared, then du is almost x dx. You would have to actually have a 2x dx. But we can handle an extra 2, that's not a problem. But note, the x to the fourth that we see in the denominator, we could write that as x squared squared. So let me go ahead and rewrite this a bit before we do a substitution. This is a definite integral from 0 to 1 of x dx over 1 plus x squared squared. So the x squared in the bottom is our u. X dx would be not du, but 1/2 du. So going from all x to all u, we have a 1/2 that we'll pull out front, and we're integrating 1 over 1 plus u squared. And that is most definitely a familiar antiderivative. But recall, every substitution with a definite integral requires us to change our limits of integration. So lower limit of 0, upper limit of 1. Our new lower limit would be u equals that x value squared, so still 0. Our upper limit would be u equals 1 squared, which is still 1. So note in this case, our substitution has not changed the limits of integration, but you still need to show this work so that I know you've gone through that thought process. So evaluating this definite integral, antiderivative of 1 over 1 plus u squared is arctangent of u, and we need to evaluate this from 1 to 0. That is, 1/2 is a constant hanging around out front. Arctangent of 1 minus arctangent of 0. And both of these are common values, so we do need to take this at least one step further. And I would like you to pause the video and write down for me the values for arctangent of 1 and arctangent of 0. So I think the arctangent of 0 is maybe the quicker one. Arctangent of 0 is 0. Arctangent of 1 is going to be some angle theta where tangent of theta equals 1. Because remember, the inverse tangent undoes the tangent. And what is the angle between minus pi over 2 and pi over 2 where tangent is 1? Pi over 4. That's where sine and cosine are equal to each other. So the value of this definite integral is pi over 8. And as I mentioned, I think this is a nice technique and involves some good reminders, so well worth our time to go through it. Now moving on, if you have not taken some time to work through the associated class worksheet, this would be an ideal time for you to do so. At this point, I'd like to summarize problems 1b and 3b, but of course there's plenty of other good problems and you can find those associated solutions on Canvas. So working with 1b, This is similar to some problems we encountered in our first video. We need to work from the inside out. We think of an inverse trig function as being an angle. That is to say, theta is equal to arctangent of root 2 whenever the tangent of theta is positive root 2. That describes an associated triangle. Tangent is opposite over adjacent, and if you do the quick algebra, the hypotenuse must be the square root of 3. So in terms of using our right triangle, we have sine of 2 theta. In its current form, we can't really work with this. But this is where you need to recall a double angle formula that we recently encountered. The double angle formula for sine of 2 theta, which I believe we encountered in our previous class worksheet, is 2 sine theta cosine theta. And we know both of those values from our right triangle. Sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And you could most definitely leave it in this form. I am 100% okay with that. Or you could write it as 2 square roots of 2 over 3. So once again, we've seen this double angle formula for sine, so it is something you should be familiar with. For our remaining example 3b, this is in a sense similar to what we started our discussion with today. What I want to observe is somehow can we relate this to an associated looking formula? It looks an awful lot like this arcsine formula. But it's not quite in that form, but we can get it there. Because note, e to the 4x, using properties of exponentials, is e to the 2x quantity squared. So if u is e to the 2x, du would be 2e to the 2x dx. So the e to the 2x dx, making up the numerator, is really going to be 1/2 du. So this works out almost too good to be true. 1/2 is a constant that pulls out front, and what we're left with is 1 over the square root of 1 minus u squared. So immediately with our substitution, we are in that desired form. So one of those examples, at first glance, it can look extremely difficult or challenging, but if you have that right perspective or approach, you can very quickly turn it into a very reasonable antiderivative. So the antiderivative would be arcsine of u, and then we have our plus c. And as we have a substitution with an indefinite integral, we must resubstitute. So what we are left with in this case is 1/2 arcsine of the quantity e to the 2x plus c. And as usual, I would urge you to continue working through the worksheet. If you have questions, check for those solutions on Canvas or drop me an email. Stay tuned. Take care.